Imagine a system that organizes its own operating logic, assembling order out of a chaotic cloud of data. This table tracks the Palm 540B model's performance, revealing a specific anomaly, a zero-shot model matching and beating a few-shot baseline. In classification tasks, the self-prompting system, USP, achieved 73.8% accuracy, while the traditional baseline using human-labeled examples reached 73.3%. This result challenges a long-standing assumption in machine learning, the belief that high-fidelity inference requires human-labeled training examples to guide the model. The source of this data is a 2023 paper from researchers at Google and the University of Oxford, titled Universal Self-Adaptive Prompting. USP operates through a specific mechanism, an algorithm that allows the model to generate, score, and filter its own pseudo-demonstrations before processing the final query. By generating its own pseudo-demonstrations, USP removes the manual labeling bottleneck, allowing high-performance prompting to be applied to tasks where no human-verified examples are available. Standard zero-shot prompting is often unreliable because a lack of specific direction leads to high variance in how the model interprets the task. Previous attempts to reduce this variance, such as self-consistency and COSP, faced significant technical hurdles. Self-consistency requires generating multiple responses and aggregating them for every query, which makes it prohibitively expensive in terms of computational resources. COSP is more efficient, but it is highly task-specific, often failing to operate outside of narrow reasoning queries. These limitations forced engineers to choose between high compute costs or narrow use cases, creating the need for a more versatile, universal approach. The USP algorithm pipeline begins with raw, unlabeled test queries. The system samples a subset of these queries and feeds them into the model to generate a diverse pool of candidate responses. During this phase, the model is set to a non-zero temperature. This forces variance, ensuring the LLM explores different ways of answering, rather than repeating the same text. However, high-temperature generation carries an inherent risk. It frequently produces hallucinations and low-confidence data. This creates a noisy, unfiltered pool of data, lacking the reliability of human-curated few-shot examples. While generating this raw data is simple, feeding it back into a prompt without a rigorous filter would typically degrade the model's accuracy. USP solves this using a task-type adaptation node. This component identifies the query's nature and routes the candidates into one of three paths: classification, short-form generation, or long-form generation. In the classification pathway, the system must determine which candidates are most likely to be correct. USP applies a mathematical heuristic to filter these candidates. It calculates the entropy of the model's class probabilities. Lower entropy serves as a mathematical proxy for higher model certainty. Candidates with the lowest entropy are retained, while uncertain predictions are discarded. The filter also enforces a balance requirement, ensuring the selected candidates represent different classes or categories. This prevents the model from developing a bias toward a single output type based on the examples it just generated for itself. Using entropy allows the model to act as its own judge, culling weak data and retaining only the most mathematically certain predictions. For fact-based questions, the system shifts the architecture to the short-form generation pathway. Here, the scoring mechanism measures the frequency of exact match outputs. If the model generates the same short answer multiple times, that consistency is used as a reliable indicator of factual accuracy. The third pathway handles long-form generation, such as document summarization. Exact match frequency is useless here, as the model will rarely generate the same long-form text twice. Instead, USP uses Rouge scores to measure structural similarity across repeated generations, selecting the most consistent summary. This demonstrates USP's core innovation, deploying distinct mathematical filters that are calibrated to the specific requirements of the prompt. Once filtered, the highest scoring candidates from each pathway are collected into a pool. These outputs are now ready to serve as pseudo-demonstrations. The system injects these pseudo-demonstrations into a final prompt template, which is then fed into the model for the final inference. This constructed payload functions like a few-shot prompt, but without the cost of human data labeling. The model has successfully bootstrapped its own high-fidelity in-context learning environment. The empirical data proves this system is viable for more than just simple data sorting. On the big bench hard reasoning tasks, performance improved from a 49.5% baseline to 54.2%. If a model is poorly calibrated, the entropy scoring heuristic fails, causing the filtering process to retain inaccurate data. Additionally, USP's performance has not yet been extensively tested on non-text tasks, such as code generation. USP acts as an amplifier. It cannot fix a weak base model, but it can maximize the output of a highly capable one. USP represents a shift in methodology, moving away from the manual curation of examples for every new AI task. For enterprise applications, this reduces the friction of deploying models in specialized domains where labeled data is non-existent. The discipline of prompt engineering is evolving from writing static instructions to architecting dynamic, self-evaluating systems.